today's lecture is all about black holes, a very interesting topic both in physics and astrophysics. Many great physicists have solved many complex phenomena type problems related to black holes, just like including Roger Penrose and Professor Stephen Hawking. So we are going to discuss about what actually are black holes. And the concept of black holes dates us back to the time of Sir Isaac Newton, when there were two theories about light, and both of them sometimes were equally given the right hand values. So the one theory was that light is made by a stream of particles. So you can consider light to be a stream of particles. And the other theory was that light behaves like wave. Light itself is a wave. Now the problem with the wave theory was it could not tell us that how would light respond when acted by gravitational force. So you have the earth. Since we know any cannonball fired from the surface of earth goes up and then reaches certain kind of speed, and many times it doesn't escape the atmosphere of the earth, then many times they can. So the minimum speed required to escape from the surface of a planet is called the escape velocity. Then light can eventually go out of the earth's atmosphere because its velocity is very high. But in the wave theory, there was problem how light it responds to gravity because it is not a particle. But when you consider the particle theory of light, which even Sir Isaac Newton favored, then light could respond to gravity. So gravity would slow down the speed of light. But there were certain other problems with all this modern and Newtonian theory of gravity. So what happened that in 1783, John Michael, a physicist philosopher, he wrote a paper. In that he pointed out that there may be even such kinds of stars which will be so massive and in so small size and radius, so much of the dense, is nearly infinitely dense, then even their gravitational field, gravitational force will be so high that not even light could escape from the surface of a star because light doesn't go with infinite speed. Light has some finite value of speed, that is c in vacuum, nearly 3 × 10⁸ meters per second. So we would not be really able to see those kinds of stars, and because no light really escapes from the surface of a star. But still there were problems between Newtonian theory of gravity and about all the light escaping from the stars. So the problem is solved by Einstein's general theory of relativity, what you and everyone know. It is really great theory of gravity given by Sir Albert Einstein. But before studying how black holes are formed or how they die, we need to study about the life cycle of a star. That how is a star formed and how does a star become old and how it eventually dies. So a star is formed when a large amount of hydrogen gas is collected in one place in our universe, and due to the gravitational force between all of them, they come together and form a kind of structure. Now since the gas molecules collide each other here and there, and therefore heating up the other gas molecules and heating the gas, hydrogen gas itself. But when the temperature becomes great enough, and now they collide, they no longer bounce off to each other. Instead, they combine and form the helium gas. And during this kind of nuclear reaction, there is heat and light emitted from the reaction from the star which has just been formed. And that is the heat and light what we take from all of the stars in the night sky and from our very own star, that is our sun, which scientists name even Sol, and in the day sky. So like this continues for millions of years, for thousand millions of years, until the star has enough hydrogen or whatever of its nuclear fuel. But it is also possible that the star will end up by its nuclear fuels that are converting hydrogen to helium and releasing heat and some kind of light during this process. What happens that when a star ends up by its fuel? Now actually what happens in a star, since the star's gravitational force is very high and all of the particles spread out in the star try to come to the center of a star because there is so high gravitational force among them. They try to come all together to the core of the star. But this is balanced by another force, another pressure. The pressure is generated by the light and heat coming out of the surface of a star. This is just rather like a balloon, since there is tension force that makes the balloon nearly go inward, and there is another atmospheric pressure of air in the balloon that tries to make it expand, and they nearly cancel each other and the balloon remains unstable. So the same thing holds for the star. The pressure of all of the heat and light tries to cancel the gravitational attraction between the particles and molecules and atoms of the star. And the star remains unstable. But what happens when the nuclear fuel is ended up? So when it ends up, there is now no pressure of heat and light coming out. So the star will try to go inward, try to collapse in its own gravitational field, gravitational influence or gravitational force between all of its particles and atoms. What would happen next? So this was actually, the problem was solved in 1928 by an Indian graduate student named as Subramanian Chandrasekhar. And according to Subramanian Chandrasekhar, he is very great physicist and he has also won Nobel Prize in 1983. But actually he had solved the problem in 1928. So he said that according to Pauli's exclusion principle, if we try to apply to the star that is about to die now, so it is possible to support the star, its own life against its own gravity. What happens that when the star will try to collapse, when it tries to collapse, so there will be gravitational attraction and then what it actually tries to collapse, because now there is no heat and no light pressure that is going outward the surface of a star. But when the atoms and all the subatomic particles get very near each other, they all will have different velocities according to Pauli's exclusion principle, because two particles cannot have the same state, same quantum state at the same time. So they all have different velocities that will try to bounce off here and there. So this will try to make the star expand. Now this tries to make the star expand, while gravity wants to make the star contract. So what will happen the next? They two balance each other and the star again remains stable. Now this is the same way how the pressure of heat and light was balancing gravity. Now Pauli's exclusion principle, repulsion between subatomic particles, will try to balance gravity and the star remains stable. But Subramanian Chandrasekhar gave a limit, a mass limit for it. He said, since the theory of everything, not theory of everything, sorry, that is theory of relativity, it limits a maximum speed in the universe. That is the speed of light in vacuum. So no particle can travel at this speed of light in vacuum. So they will have somewhat speed lesser than this. And any kind of star that is having a mass of 1.5 times the mass of our own sun, means 1.5 something solar masses. If the mass of any star is lesser than 1.5 solar masses, then the star can support its life against its own gravity. This mass came to be known as Chandrasekhar limit, the discovery done by Subramanian Chandrasekhar. Now what happens next? That suppose any star is having mass less than this. So what will happen? Of course it can support its life against its own gravity. It's somewhat like this way, that there will be Pauli's exclusion principle, repulsion between all the particles, and the star will again come to a stable state. And such a kind of star in which there is Pauli's exclusion principle, repulsion between its electrons, and then it comes to a final state. Such a star is then known as a white dwarf. While such a star where there is exclusion principle, repulsion between neutrons and protons instead of electrons, like a white dwarf, then such a star came to be known as a neutron star, which have radius of only just like 10 mils or so. So their diameter is somewhat 20 mils, so it is very less. Right, a very less distance, a very less size. So their gravitational field and so gravitational force is also very high. Now what happens next? This was for the masses lower than the Chandrasekhar limit. But the problem arises, what if the mass of a star is higher than that of Chandrasekhar limit discovered by Subramanian Chandrasekhar? What would happen the next? So, according to some scientists the problem was solved this way, that the star will throw off some of the matter and some of the mass and it will become stable. But how does it know that it has to throw this amount of mass or matter to become stable? Or even if it knows, even he is genius and intelligent enough, it throws the matter. What happens if we add more mass to a neutron star or a white dwarf? Well, Einstein and Sir Arthur Eddington were very worried about it. Sir Arthur Eddington, who was really the teacher of Subramanian Chandrasekhar at Cambridge, because Subramanian Chandrasekhar later went on to study at Cambridge and to show his detailed work over the stars, over such kind of stars, and show his result about Chandrasekhar limit. Einstein and Eddington were really worried about it. Einstein even wrote a paper that the star will throw off the matter of it and it will not collapse to infinite density, because if there was not exclusion principle repulsion enough, so the star just goes under its gravitational collapse and it may come to a singularity where all the laws of science break down, where even general relativity breaks down. But Einstein was worried about it. He wrote paper, it is not possible. But then it came the year of 1983 when Subramanian Chandrasekhar was awarded Nobel Prize in Physics for his discovery of Chandrasekhar limit, a limiting mass for cold stars. Now let's first get back to the past. Actually, what actually happens when the mass of the star is higher than Chandrasekhar limit? The problem was solved by a young scientist in 1939 whose name was Robert Oppenheimer. And I am sure you must have heard about Robert Oppenheimer. He was also known as the father of atomic bomb. So what happened? Oppenheimer said, and if there is gravitational collapse for this star, since light will be always emitted from this star, from the surface of a star, but when there will be a collapse in the surface of a star, the radius goes small and the gravitational force and field goes higher. And as this happens, then the light coming out from the surface of a star will get dimmer and dimmer, the redder and redder. It will be red shifted, and finally the star comes to such a point that it will be nearly infinitely dense. And then light can never escape from the surface of such a kind of a star, and the boundary of this star is called event horizon, and then was formed the concept of what later came to be known as black holes. Such a star turns into a black hole. Now, to understand this concept better, we need to just know that in the theory of relativity, both special theory of relativity and theory of general relativity, there is no particular measure or value of time. So 1 second here is not 1 second on Pluto, right? You should be knowing this. So if you want to understand the concept of black holes well, and if you want to understand how from black holes really light is not emitted, so suppose there is there is some sort of astronaut on the surface of a collapsing star that has mass higher than the Chandrasekhar limit, and the star is going to become a black hole. And there is another spacecraft nearly orbiting around the star, and there is another astronaut in the space. Now what happens? That the astronaut who is on the surface of the star, which is going to become some sort of black hole, every second he sends a signal to the spacecraft. Now what happens? They will be receiving the signal every second, but since a star is getting smaller in size, the radius gets small, the gravitational force goes higher. So for the astronaut on the surface of a star who is so close to the star, time will be slowed down, while that on the spacecraft, for him time will be somewhat faster. So the second astronaut will have to wait more than 1 second to receive the signals, but this will be very less in fact until the star becomes a black hole. But when the star will really become a black hole, then the astronaut will have to wait forever for the next signal, even if the first astronaut sends a light signal, but since nothing can escape a black hole, he will have to wait forever. And thus he does not receive the signal. This is how a black hole works. Now, if you want to understand what if you went into a black hole, or what it would be like to be into a black hole, then you can understand it in sort of this way, that when you enter the black hole, since as the radius increases, the gravitational force decreases, and as the separation decreases, the force increases. So when you are going down to a black hole, when you are going near the singularity present inside the black hole, when you have past the event horizon, the force on your knees and your foot will be more than the force on your head, which is somewhat more separate to the event horizon, to the singularity than the foot. So here, by this way, you will be either torn apart or you will be stretched by very much amount. So this will seem rather difficult, and this seems too much of science fiction, but it's reality. But then the gravitational force becomes so high that you will be eventually torn apart. This is the concept of a black hole. But there's even more. If you want to understand how it would like to really understand about what are black holes, then you need to understand about the weak and about the strong cosmic censorship hypothesis. So what actually is weak cosmic censorship hypothesis? It is actually the work of great physicists like Roger Penrose and Professor Stephen Hawking between the years of 1965 and 1970. So it is, since we know that according to general relativity, if it is really correct and if our opinions and beliefs about general relativity is really correct, then at the singularity of a black hole, since there is infinite density, no laws of physics, not even general relativity itself that predicts the existence of black holes, even it itself cannot hold right there. So there will be a failure in predictability of the future. But anyone who is outside the black hole, who is outside the event horizon of black hole or singularity inside the black hole, will not be affected by this kind of failure in predictability of the future or of whatever the past, because outside there is existence of time, but there is no meaning of time just inside a black hole or just at the singularity, because you cannot define time before the Big Bang and you cannot even define time inside a black hole. Then comes the strong cosmic censorship hypothesis, that the singularity point either lies completely in the future or completely in the past. So this is really strange. Now let's come to the point. So how to actually detect a black hole? How can we detect a black hole? Nothing, not even light could escape from a black hole, and even John Michael from Cambridge in 1783 wrote that nothing, not even light, can escape from surface of such a star, which was later came to be known as a black hole. So how can we see of it? Well, about it, if you want to understand, you need to understand about the work of the great Professor Stephen Hawking, known as the Hawking's radiation. So before understanding Hawking's radiation, I would like to introduce to you about black hole's area theorem. It's somewhat this way, that a black hole's area always increases, and as it should. So if you have one black hole here and one black hole here, and they combine and collide to form a bigger black hole, then the area of the bigger black hole will be either equal to the area of both the black holes combined or even greater than it. So this is black hole area theorem. Now, according to second law of thermodynamics, the entropy of a system always increases. It should be always increasing. But what happens that if you throw some matter right into the black hole, there is no meaning of time inside the black hole or at the singularity of the black hole, inside the event horizon. Then how do you define all of it? When you throw the matter, then the entropy of our universe outside the black hole will decrease. And if it decreases, it really violates the second law of thermodynamics. So for a moment, it was thought that does the black hole violate the second law of thermodynamics? Then the problem was solved by Jacob Bekenstein, also a research student at Princeton. He said that the entropy of a black hole, if you want to measure the entropy of a black hole, so it's nothing but the event horizon. So event horizon of the black hole, which we call the boundary, the path of light rays that fail to escape from the black hole, is nothing but the measure of entropy of the black hole. But this was rather difficult to grasp for most of the physicists, including Stephen Hawking himself. It is because this way that if the black hole has event horizon, and event horizon is nothing but the measure of entropy of the black hole, then the black hole must have some temperature. But it was thought that it has no temperature after all. If the black hole has temperature, so as all other and like all other hot bodies, the black hole should radiate. But it was thought that black holes don't radiate because nothing, not even light, could escape from a black hole. So how could the problem be solved? Later, Stephen Hawking himself was worried about it a lot, and he thought that Jacob Bekenstein has misused my discoveries and Roger Penrose's discoveries about black holes area theorem. Then first he was angry at Jacob Bekenstein. Later he thought for it for a moment, and he started solving problem of radiation. Now there already existed theories that rotating black holes should radiate after all. But then even Stephen Hawking tried himself the calculations, and he found something really exciting and surprising, that even non-rotating black holes radiate. Now he wanted to explain this. How is this possible? Non-rotating black holes, or whatever black holes radiate, nothing, not even light, can escape from the black holes. So Stephen Hawking used quantum mechanics, and it was the first theory to use both general relativity and quantum mechanics combined, unified to each other. So it is a great leap in trying to find the theory of everything. Stephen Hawking thought of it as empty space. Suppose you have empty space right here. Now, if you really speak of space to be empty, you mean that the gravitational field and electromagnetic field, therefore, or there at the empty space to be zero. But the gravitational fields, those kinds of fields are just like velocity and position of a particle, and according to Heisenberg's uncertainty principle, you cannot measure the position and velocity simultaneously with a high degree of accuracy and precisely. So how can you tell of those gravitational and electromagnetic fields to be zero? Because if you call both of them zero, so you give a precise value of both of them. So there must be some disturbance in the field, there must be some kind of quantum fluctuations. And Hawking thought of it as by something called virtual particles, the same kind of particles that carry the gravitational field or gravitational force from the sun even to our earth. Then Hawking thought over it as, since energy cannot be created out of nothing, so Stephen Hawking thought that one of the particle-antiparticle pair, there will be particle-antiparticle pair, one of the particles should have positive amount of energy while the other particle should have negative amount of energy. Exactly the same. So at first they want to annihilate each other in a great flash of light, like how you would do if you are meeting your anti-self, like someone coming from anti-world. So if you shake hands, you both annihilate each other in a great flash of light, and you would both die, you would both disappear. So never try to shake hand to your own anti-self, right? Even if you see him. So what happens? But at the black hole, gravitational force is so strong that it can even convert the virtual particles to real particles or real antiparticles. So the particles which will be present near a black hole, or even the antiparticles which will be virtual particles after all, they will be converted to real particles or antiparticles, and they will either just go directly into the black hole, or since they were out, so they or just escape from the black hole. Now no longer is stuck at the event horizon, and when those particles will escape from the black hole, and they will be the particles you will see coming out from the black hole, and this is what black holes radiate. It's nothing like that it is coming out from the interior of a black hole, from the singularity of black hole. That is not possible. It's just the particles that just escape from the black hole, that just escape from nearby of a black hole. But you will think that the particles are coming, the antiparticles are coming from the singularity of a black hole. This seems to you, but that is not the true nature of a black hole, the true nature of reality. And this discovery was later named as Hawking's radiation, named after the great Professor Stephen Hawking, my ideal theoretical physicist whom I really like to be. I also want to do some great researches in the fields of black holes and physics, just like great Professor Stephen Hawking and great Sir Albert Einstein or Sir Isaac Newton. So this is how we can measure about black holes emitting radiation. And there is paradoxically, what happens, you can actually detect smaller black holes than the larger ones. Now this seems very strange thing, but it is somewhat this way, that small black holes will have small masses, thus higher temperature. When they have higher temperature, they will be emitting radiation at higher level, higher level. Due to what, you can see the smaller black holes and X-rays and gamma rays coming from the smaller black holes, and you cannot actually that much in front of a supermassive black hole, so it will be very difficult to form. And the interesting fact is that any astronaut, any poor astronaut who falls into the black hole, he will also come out as radiation, Hawking radiation from the black hole. So he will be never destroyed, he will become immortal, but in form of radiation, in form of mass and energy, but he will not have his eyes right there or his brain working right there to observe that he has now become immortal, he will always exist, right? After that, what happened? Hawking and even writes in his books, and there are many people who write about primordial black holes. So black holes cannot just form from gravitational collapse of a star. There are other ways. There is the very early universe just after the Big Bang. So due to irregularities in the universe, due to the very high densities, amount of density in some regions of the universe, there might be formed some kind of black holes, and those black holes are today known as primordial black holes. So since primordial black holes are not just as large in size as supermassive black holes or other sorts of black holes, then that is the reason you can easily detect a primordial black hole. Now what happens that actually black holes have been detected for now, not in the very early time as Professor Stephen Hawking or Jacob Bekenstein, but today black holes really have been detected, and even I think there was image taken of a black hole even, and Hawking radiation theory has been also proved correct. So now we have really evidence that black holes exist. Actually, to be truly speaking, before black holes were detected experimentally proved, there came so many theories about black holes. So it was nearly first time in the history of physics or philosophy that we had so many theories about a thing that had not been experimentally proved yet. But since general relativity is correct and even quantum mechanics, then black holes really exist, right? There are some sort of black regions in space.